Okay, in this video we're going to introduce the law of sines. But before we get into that, let's kind of review something we've done before, right? Where we are talking about solving triangles. All right, so when I mean by solving a triangle, that means that we know all three sides, all three angles. And then once we know all those pieces of information, then you have solved the triangle. Now, we've done this when using the Pythagorean theorem, but again, that only applies to right triangles. Right? So far, right, the way we developed all of our trigonometric functions, it was what we called right triangle trigonometry. So as an example, right, we had this triangle here, right? Right triangle. The opposite sides of hypotenuse, and we all usually labeled A, B, C, right? Where A, B corresponded to the legs, right? And then C was the hypotenuse. And we have these angles, we'll just call these alpha and beta. Right? And let's say, for example, that I was given that B was 4 and C was equal to 7. Right? So I do need to be given some piece of information to start. Right, and this is enough information, right? I do know one angle, 90. Again, that allows me to use my trig functions, right, by using opposite over adjacent, stuff like that, sine, cosine, or tangent, depending on what values for the legs that I want to use with the corresponding hypotenuse. So the first step, like let's say we were asked to solve, like let's say here the example was take this triangle and solve. Right, the first step would be to let's find the value for A, right? And I can do that using the Pythagorean theorem. Right, now here I want to stipulate again, and I'll probably say this over and over, that this only applies to right triangles. Okay. All right, so if I know that it's a right triangle, that information is given to me, then I can use this Pythagorean theorem. Otherwise, it is an invalid theorem. Okay, so what I would do is I would plug in, right, A squared, B is 4 squared, C is going to be 7 squared. All right, and we get A squared plus 16 equals to 49. All right, subtract 16, and we get A squared is equal to 33. Take the square root, and A is plus or minus, but when we're dealing with length, always positive, right? So I won't even bother writing the plus minus here. So we get A is root 33. And the only factors here are 3 times 11. None of those are perfect squares. So I have this here in reduced form. So A is root 33. All right, so I have all the sides. So we got that so far in solving for this. I don't have an angle, or excuse me, I have an angle, 90 degrees. I need to find alpha and beta. All right. Now here is where our right triangle trigonometry comes into play, right? We could say, all right, well, depending on which one you want to be the reference, I could say something like sine of alpha. All right, and again, I just chose sine because it said cosine, and even tangent, right? I know all the sides. So using any 3 of these will actually lead you to the same result. All right, so sine of alpha, what is opposite over adjacent? Excuse me, opposite over hypotenuse. So that would be root 33 over 7. All right. And then here, right, at this point, right, this is nice. We're incorporating a lot of the stuff we've already learned throughout the course. Right, this is true if and only if arc sine of root 33 over 7 is equal to alpha. All right, and then now you have a calculator out. Let's see, all right, let's say second arc sine of square root 33 divided by 7. And here, let's work with degrees here. Since our examples using the law of sines, we're going to go back to using degrees exclusively. So I'll make sure I'm in degree mode. and then we get 55. We'll use one place value, so we'll get alpha is approximately 55.2 degrees. All right, so we'll call alpha 55.2 degrees, right? Just round it off to one decimal place value. All right, good. So I know one angle already, 90 degrees. I found another one, alpha, that's 55.2 degrees. All right, so I'm almost done, right? I have all three sides, and the only thing missing is beta. Now I can use another trig function, but there's another way to do this that is much more straightforward. All of the angles of a triangle, at least in a plane, must equal to 180 degrees. So actually, I don't need to do any more trig. I can do a simple subtraction problem where beta is going to be, there's 180 degrees total in all the angles. I know one of them is 90 degrees. That is from a right angle. And I know the other one that I just found is 55.2 degrees. And here, the third one must be whatever is left after subtracting 90 and subtracting 55.2. So here we have 180 minus 90 minus 55.2. And we get 34.8 degrees. Okay, so I saved myself a little bit of work here, right? Without having to deal with another trig function or the inverse trig function, by just remembering the fact that the sum of all three angles in a triangle in a plane, right, is always going to be 180 degrees. All right. Okay, now this is all great, right? This is something we've done before when we had a right triangle. Again, remember, this is only valid for a right triangle. Right? What if I don't have a right triangle? All right, what if in general we have, let me introduce here, excuse me, let me get a straight edge out. Let's say that we have some non-right triangle. All right. Okay, and we don't know any kind of relationship between the sides in terms of they don't necessarily have to be equal. They're not. It's not equilateral. It's not isosceles. There's nothing special about this triangle. Maybe all three sides are of different lengths. Right, so we're going to introduce the law of sines, but before I get to the introduction of it, I just want to introduce a general kind of labeling of a triangle here that we're going to see, right? It's kind of standard used throughout, definitely our textbook and other textbooks, you'll use the same kind of formulation, where we'll label these sides A, B, C, right? And then the angle usually that goes across A is labeled as alpha. The angle that goes across side B, usually called beta. And then the angle across C is this angle called gamma. All right. Okay. And then sometimes we'll even see the formulation of the corners where you have A, B, and C. All right, capital A, B, C. And this is really in geometry, if we want to, we usually label this shape triangle A, B, C. Right. But for our problems here, we'll usually deal with naming the angles and the sides using these Greek letters and the lowercase a, b, c. All right, so if we were to ask to solve just a general triangle, again, we are not necessarily, it might be right, but actually we don't know. In a lot of cases, it won't be a right triangle. Now, one tool that we have available to solve a triangle like this, it's what is referred to as the law of sines. All right, now the law of sines is a ratio between the sine, clearly it's in the name, of an angle and its opposite side. All right, so for example, the law of sines states that the following quantities are equivalent. Sine of alpha over A is equal to sine of beta over B is equal to sine of gamma over C. All right. Now, here we have three parts to this equality here. So all this is saying is that you can take any of these. You could say you can use this equation, right, to have our standard equation where we solve for a value. You can have this equation, right, or you can omit the middle term. And you can have this outer equation here, sine alpha over A equals sine of gamma over C. All right, so any of those would work that you can work with, right? Which one do you use? Well, it depends on the information that's given, right? Now, if you notice here, if we are going to solve for a value, right? Because the goal here is that we're given some pieces of information from the triangle, right? But not all of them. It's up to us to find the rest of them, right? So here, if I wanted to use this, I would probably need to know, well, I would probably be given or found three of these values and solve for the fourth one. Right? So as we notice that there are some limitations as to what we can use here. So if we have, so not every information that's given us for a triangle automatically applies the law of sine. So for example, what I mean by that is, let's say that I knew A, B, and C, the length of the sides. Well, that's not really going to be helpful here, right? Because I need to have just a pair of these. I need to know at least here one angle. And if I'm just given the three sides, the law of sines will not be, the three sides, the law of sines will not be appropriate here. Okay, so this would work for certain cases. And so not for all cases. So cases that do work, right, is if I knew two angles, right, and the corresponding side, right? So usually we label like this angle, angle, side. So what that means is I have an angle, and then this side here, right? Or again in this order, angle, angle, and then the side opposite that first angle, right? Or angle, excuse me, angle, angle, and the side opposite that first angle. Or here, angle, angle, and the side opposite that first angle here. Okay, that would allow me to use that, right? So we have three cases here. Again, the A stands for angle, the S stands for side. Another case that would be useful is the angle side angle, where we can use the law of sines here. And here if we have, let's say, angle, the included side, and then another angle, right? And again, this doesn't necessarily have to be these here. It could be this angle, this included side, and then the other angle across the way. And there is a third case that we could use the law of sines, and that case is the side angle. All right. Now, this one is a special case. This one is called the ambiguous case. Right, because of the nature of the value of the sine and the inverse sine, right, there is a possibility when we have the ambiguous case that we have either zero solutions, or zero triangles essentially, one triangle, or even two triangles. Right, and we'll get to that in a later video here for this module. Right, but these other two define a unique triangle. Right, so the ambiguous case, we may have zero triangles, one triangle, or two triangles. All right, and these two cases define one, each one of them defines one each one defines one unique triangle. Okay. Now you might be thinking, well, there are other kind of combinations here that we might have, right? So let's say we have all three angles, right? In which case, as we've seen before, right, the law of sines will not apply, because we need, if we have three angles, there's no way to solve for one particular side, right? And in fact, if we only had the angles, there are really an infinite number of triangles that you can come up with that are all congruent with the same amount of angle, with the same measure for each angle. Okay, all right, thank you.